On these examples, we're going to be calculating the areas underneath a curve. And to do so, what we're going to do is go ahead and set up the definite integral. So part of this is going to be fairly easy. This first one I picked out isn't too bad, but the second one is a little bit more challenging. So let's start out with this definite integral. All right, it's from a to b of f of x dx. So we need to identify, first of all, our bounds of integration, a and b. So these are x values. What x values do we have on the shaded region? Well, it looks to me like we go between 1 and 3. Now, a is our lower bound, so that's going to be our 1, and b is our upper bound, so that's going to be 3. Next up, let's go ahead and try to identify what is our function f of x. And it looks to me like it's this nice line going down here. So that line, we're going to need y equals mx plus b, where b is our y-intercept. So in our case, b, our y-intercept here, is going to go with 4. And then m is our slope for this line. So we're going to visualize this as rise over run. Now we have one point, that y-intercept. We need to identify another point on our graph. You can pick any point that's easy to locate. So in my case, I'm going to go ahead and point towards this one that's right here. To go from the y-intercept at 0, 4 to that point at 1, 3, we're going to go down 1. And we're going to go to the right one. So when we're visualizing this as rise over run, going down is going to be a negative, and going to the right is going to be a positive. So negative 1 over 1. Overall, we can say our slope is going to be negative 1. So filling that in, m is going to be negative 1. I'm just going to put a negative in front of the x. I don't have to include the 1 if we don't want to. Plus 4. So negative 1x plus 4 is our function f of x. Finally on this, what we're asked to do is find the area of the shaded region. So the area of the shaded region, what I'm going to do is I'm going to visualize this as a triangle, basically in the top, and a rectangle in the bottom, and use some of these basic formulas that hopefully we've seen before to help us out. Now let's start with the triangle first. Now we know it's 1/2 base times height. So it's going to be 1/2. Our base here goes across two pretty clear units there between 1 and 3. And then the height is going to go 2 units between 1 and 3 also as it works out here. Okay, so 1/2 times 2 works out to be total of 2. But we also had, at the bottom, we had a rectangle. So that rectangle is just length times width, or base times height for its formula. Well, it has a base of 2 and a height of 1. So overall, this is going to be an area of 2. So 2 plus 2, we're going to end up with a total area of 4 units, 4 square units, I suppose we should say. So now we got that one out of the way, let's take a look at a little bit more challenging problem. It looks very similar from the beginning, where we have to identify our lower bound and upper bound of integration here. So again, that's 1 and 3. Don't think that's too difficult to pick out where those come from. But then creating the equation for this line. Again, it is a line, so that's kind of nice. I don't know if you can tell that's going to have a y-intercept. Remember, thinking y equals mx plus b. Our y-intercept is going to be 5. But what about the slope? Again, the slope of this line, we're going to visualize it as rise over run. I've got one point up here at 0, 5. The next point that I can really be confident about on this line appears to be all the way out here at 4, 4. So thinking, again, rise over run. To go between my y-intercept and that other point, we'd go down 1, but this time we'd go right 4 units. Okay, so down 1, right 4 units, negative 1/4 is going to be our slope. So we can answer this what is f of x question as negative 1/4 goes in for m, our slope, times x, plus our y-intercept 5. Not too bad. But now what about the area here? The area is the most challenging part here. So I'm going to get rid of this work, and let's visualize what this is going to look like. So I'm going to zoom in a little bit. The area here, if we split this up into a triangle and a rectangle again, we can go back to our basic formulas, 1/2 base times height for our triangle, and just base times height or length times width for our rectangle, but it's a little bit more challenging. Okay, let's try to simplify this a little bit because we know f of x is negative 1/4 times x plus 5. If I want to know the height of this point over on the right-hand side, that's going to have an x value of 3. If I evaluate 3 into our function, if I plug it in for x into that function we just created, we know that that is going to have a height of, it looks to me like that's going to be 4 1/4, 4.25. So this side is 4.25 high. What about this other point over on the left-hand side? This highest point of our triangle over here? Well, that occurs at an x value of 1. So if we want to figure out the height that goes with it, we substitute or evaluate a 1 into our function. We get negative 1/4 times 1 plus 5. That's going to be 4.75. All right. Next, what we want to do is figure out if this is 4.75 high and this is 4.25 high. If we do a quick subtraction, hopefully we're going to get that that is 0.5 or 1/2 a unit high in between those two. All right, so that's all the information we kind of need. We just need to put it together. This triangle is going to be 2 units across. So the area of that triangle is going to be, again, 1/2 base times height. I know I'm mixing up fractions and decimals. It'll be okay, though. So that's going to be 0.5 or 1/2 for its total area. And then the area of our rectangle down here is just length times width. Well, the width is 2 units wide between 1 and 3. What about the height of this rectangle? Well, we did that calculation when we found the height of that point when we plugged in a 3. So that height was 4.25 as we labeled it over on the right-hand side. So this area is 8.5. If we put these two values together, our 0.5 for the triangle and the 8.5 for the rectangle, these sum up to 9. So that's going to be the total area of our shaded region. Now I tend to split these up into triangles and rectangles as much as possible. If you did this another way using a different formula, good luck to you. Nothing wrong with that. It's just I prefer to go with the basic formulas because I find them pretty easy to memorize for rectangles and triangles. Hope this helps out. Best of luck to you as you work through these and try to set up definite integrals.